Hey folks, welcome to this channel and welcome to this video. I'm Saptarshi. I'm a software engineer 3 at Google and a competitive programmer. So in this video we are going to look at the problems that came today in the Leetcode weekly contest 405. We have 4 problems. The first 1 or 2 problems are quite easy. Just a bit of implementation things in the second and third problem. And in the third problem you need some dependencies across sub-problems maybe. We will look at those things. And the fourth problem is a good one, which actually explores some good data structures, some good algorithms. The fourth one is based on dynamic programming and tries. So let us now take a look at these problems. So the first problem is basically find the encrypted string. It basically says that, hey, for each character in a string, replace it with the kth character after that. So each character gets replaced by the kth character after that. Now let us see. Let's say over here, this is a given example, the word DART with the k of 3. So D will be replaced by the third character after it. First, second, third. D gets replaced by T. A gets replaced by the third character after it. So 1, 2, 3. The third character after it, that is D. R gets replaced by the third character after it. So 1, 2, 3, A. And similarly, T gets replaced by the third character after it. Okay. T gets replaced by the third character after it. So D, A, R. So in this way, TDAR is found. Now, if you look at it minutely, what we have done is we have rotated the string. This is known as a rotate operation, and you have a classical problem of rotating a string. Rotate a string by k places. This is a classical problem which has to be solved over here. So yes, one way is basically form a new string, and for each character in the string, for each character, let's say 0th character, look at what is the 0 plus 3th character over there. So for 0th character, look at what is the 0 plus 3th character in the original string. So third character is basically T. So T comes over here. For first character, basically look at what is the 1 plus 3th character. Here you have to be careful. Instead of 1 plus 3, you should basically do a modulus by the length of the string, because you are doing it cyclically. So 1 plus 3 modulus 4 gives you 0th. So it is a 0th character that you look at. What is the 0th character of the original string? That is D. And in this way it continues. So in this way you can fill up a new array by converting that. So you want the ith character, you will go to I plus k modulus n, that index of the original string, and get that. So your new string, if I name that as ns, ns of I will be equal to s of I plus k modulo n. So this you have to do for all the I. S of I plus k modulo n, where s is the original string. If you do this, your problem will be solved. What different thing you can do is, you can make an observation, which is actually used in this problem to do it in place. Here you need a separate array for the new string. Here you can do in the original string only, if that is mutable. If that is something like a character array, you can make the change over there only. So you can look at it something like this. But let's say k is equal to 4. So 4 times rotation means your S will go, okay, E will come over here, R will come over here, and then so on, S, P, I, D. This will be the answer for k equal to 4. Now if you see what really happened, the first 4 characters, the first k characters went to the last k characters. If you look at it, the first 4 characters went to the last, and the last remaining characters came to the beginning. So here you have the first 4 characters coming to the last 4 characters, and the remaining characters, n minus k characters, staying at the beginning. So this is something like, looking at this, we can actually plan some strategy to do it in place. The observation is that, hey, when do you see that the first character going to the end, the last character going to the beginning, towards the beginning? When do you see that? If you reverse the string. So that is the idea that is followed. That hey, if this is what you have to do, you have to send the first k characters to the end, the last n minus k characters to the beginning. Then take that string, spider, and first reverse it. First reverse it. What do you get? You get redis, something like this. Now, you can see that the first k characters came to the end as you expected, and the last remaining n minus k characters came to the beginning. But they are in the reversed order. You need in this order, they are in the reversed order. Instead of SPID, you have DIPS. So, okay, you know that the last n minus k characters have come to the beginning. So, up to n minus kth index, from 0 to n minus k minus 1, you can do the reversal. You can do a reversal here. Do a reversal here. You get something like ER. Again, do the reversal here. You get something like SPID. So in this way, your original string gets formed. You have done 3 reversals only. So yes, this is a good code in the sense that you can do it in place. Reversal is an operation possible to be done in place. That is, in the same array, you just keep on swapping few characters and it gets reversed. There is a popular two-pointer approach which we can use in the implementation. And then you do this reversal 3 times. One time on the whole array or string, and 2 times after that on 2 other parts of the array. Thus, in 2n steps, your solution basically gets completed. So let us look at the code. So you can code somewhat like this. You can code a reverse function which takes 2 pointers, start to end. From start to end, it will do the reversal operation. So while start is less than end, we will reverse the start and end, and then we will make them come closer. So we started the 2 boundaries, reverse them, then we come closer, again reverse those 2 characters, come closer, reverse those 2 characters. In this way, the entire thing gets reversed. So this is how we reverse any part of the string, and now you can call these 3 times. Reverse from 0 to n minus 1, reverse from 0 to n minus 1 minus k, that is n minus k to n minus 1. And you can do this in a different order also. Like initially, you can do that reversal over here. You can reverse this part, or sorry, you can reverse the first k characters, the first and the last n minus k characters, then reverse the whole thing. That also can be done. It's totally fine. And there is one more thing here. It is not given that k is always less than n. If k is equal to n or greater than n, then that may become a problem for you. So here k can go up to 10 to the power 4. Your string length is only 100. So then, this n minus k minus 1 basically will lead to some errors or wrong answers, whatever. So if you know that k is bigger, if let's say n is 100 and k is 103, you know that that first 100 turns will not add any change. So 103 basically means 100 plus 3. If n is 100, that means the first 100 rotations will add no change. So you can do this operation of k modulus n, and whatever remains, do that many rotations. Do rotations for that many things, because the first multiples of n, whatever multiples of n is there, for that there is no net change in the string. So yeah, that is the way you can solve this problem. Pretty short code, and you can do it in a simpler way as well. This is a different way of coding it. This is a classical problem, so yeah, good to know this. Okay, now let us look at the next problem. The next problem basically says that we need to generate binary strings of length n, which follows a certain feature, certain property, that all substrings of length 2 contain at least a single one. That is, in every 2 consecutive characters in that binary string of length n, binary string means a string in which there is either 0 or 1, like zeros and ones basically present, no other character. So now there should not be any 2 consecutive zeros, because if there are 2 consecutive zeros, then you have at least a single one present. So yeah, that is what we can use in our strategy. So the way I would look at this problem is we need to go up to all the, we need to reach all the binary strings of length n. Now what are there? What are possible? If we basically say n is something like 3, n is 3, and what are the numbers possible? We can have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now if you look at this, here you have two consecutive zeros. There is no 1 in this substring, so this is cancelled. This is not valid. Similarly, two consecutive zeros cancelled. Here there are no two consecutive zeros. Each substring of length 2 has at least a single one. So it is good. This is also good. Here again two consecutive zeros, so bad. This is valid. This is valid. This is valid. So up to where do you need to go? You are starting from 0. 0 is always the first number possible. The last number of n digits. So if you know a bit of bit manipulation, you know that the last number of n digits can be represented as 2 to the power n minus 1. So from 0 to 2 to the power n minus 1, I can say that for each number, if you find out the binary equivalent, so this is the binary equivalent of this number. So for each decimal number from 0 to 2 to the power n minus 1, if we find out the binary equivalent, then we can basically parse through that and check whether that is valid or not. Or while forming that binary, like when I'm looking at 4 and I'm forming this binary, the moment I see that I'm getting two consecutive zeros, like you all might know the decimal to binary conversion, I divide by 2, I look at the remainder, and this is my quotient. So remainder is 0. Then again I divide by 2, I look at the remainder. If 2 times consecutive you are getting the same remainder, 0, then you can say, okay, this is invalid. So while looking at this, you can basically say this is invalid as per the question. As per the question. So yeah, so using this we can solve it. So let us see how I've coded it. By the way, before that, the constraints. You will see in the question that the extent of n is mentioned. That will tell you how much this 2 to the power n is reaching. N goes up to 18. So you can say, okay, if n goes up to 18, that means 2 to the power n basically goes up to 2 to the power 18, which is somewhere around 10 to the power 6 divided by 4, something like that. I mean, roughly equal to slightly more than that. And now we will, for each such number, we will basically parse through all the digits. Number of digits is, you can say 18. So 10 to the power 6 divided by 4 multiplied by 18. That is pretty much less than 10 to the power 8. So you can happily do this. If you have less than 10 to the power 8 operations in total, you can do this. So let us see how we have done it. I've used the string builder class at different places. String builder basically helps us to do operations on string very effectively without adding extra time complexity. So you can start using string builder if you're coding in Java. So yeah, I've created a list. This is my limit, 2 to the power n minus 1. 1 left shift n is just another way of writing 2 to the power n using the bitwise operator. Then I am going from 0 to that limit, and for each I am taking it in car. I'm having some variables. We will see these variables, and I'm starting with a value 0. I think I'm not using this value. You can ignore this. I'm storing that value of the binary in SB, the string builder object, which is basically building a string. Now I'm remembering this n. I think okay, yes. So I am basically running this loop for n number of times so that I can generate n digits always. So I'm taking it in a variable and taking this up to 0. X minus 1 is greater than 0. Now I get a character, car modulus 2. I'll check whether that character is 0 and the last character is also 0. I'll store the last character. What was the last character? So it starts from minus 1, so that in the beginning I'm not basically expecting something before, so I'll store this as minus 1. And now later on I will store this as d, whatever is this character. If I find two consecutive zeros, I will say flag equal to true break. It's done. No expectation. If not, then I'll continue the usual binary thing. So this thing, if you just leave this thing, then the remaining thing is decimal to binary conversion. except how many times we are doing it. This thing sort of, we have to do a different number of times. So this will give you the reverse of the binary equivalent. This will give you the reverse of the binary equivalent. So you come out, you see whether the flag is true or not. If the flag is true, that means this saw a violation, then directly continue. Otherwise, reverse the thing. This will give you the reverse of the binary equivalent. Because basically, in our binary thing, we have to read the answer in this way. The last thing that comes will have to be read first. When you do append, last thing that comes will come last, will get appended last. So you need to reverse it to bring it to the first. You need to read this one first, then this one, and then this one. So that is what I did using sb.reverse. Yeah. And then you add list.add sb.toString. In this way, that string which passed through your test gets added to the list. You just return it. So this is what you do. ToString, this is how it gets converted to a string. So yeah, you can see the statistics. It beats the runtime and memory both by 100%. And though, I mean, I think it talks only about Java, is it? Whatever, regardless. But this basically follows the right time complexity and space complexity measures, optimization measures. So yeah. So let's look at the next problem. This had a bit of bit manipulation in it, so it was a good contest actually. It helps you revise a number of small things through fairly easy questions. Now the next problem. The next problem is basically around, you have a grid. Each cell contains X or Y or dot. Now return the number of submatrices that contains the first cell, an equal frequency of X and Y, and that frequency should be at least 1. So look at this, XY dot, Y dot dot. This is one such thing, this is another such thing, 2 submatrices, this is also another valid submatrix, XY dot. So equal number of X and Y, it includes the first cell, and the count of X is at least 1. So that means this the third thing basically means at least 1 X basically means that all cannot be dots. Second thing means that X and Y count should be equal, each should be greater than or equal to 1. The first thing is very interesting. Without this, solving this would have been far more difficult or far more complex in terms of time complexity and space complexity. By this you know that okay, the submatrix that will be your answer, or whatever submatrices you will be counting, they will always start at 0, 0. So yeah, so basically taking 0, 0 at the starting point, you can maintain a prefix kind of a thing, a prefix information. But okay, up to this point, what is the total number of X and Y I get? This is a common kind of a strategy because that is what you need. The starting is given. If the starting was not given, then you have to form a different kind of a way. But submatrices with a common starting point basically becomes a prefix kind of a thing. So you have this kind of a matrix, let's say. Every submatrix has to include the first element. So if I ask you about this submatrix, then I'm basically asking you, hey, what is the prefix for this? For any, let's say this matrix is MAT. So for any MAT IJ, or you can say this is the answer, yeah, or let's name it as the answer. Sorry, you can say the sum matrix. We are interested in this sum of, for your row going from 0 to I, your column going from 0 to J, you are adding the summation of your grade RC. Now for what are you basically adding? You can see you'll maintain separate thing, sum X, sum Y, those kind of things. So you'll maintain that summation in this way, sum X, So that will be basically counting, hey, if grade RC is equal to X, then count 0, otherwise count 1. Then count 1, otherwise 0. So in this way, yeah, in this way, uh, you can basically keep on adding all the X up to a point and you can maintain it somewhere. Now for matrices, how do you use this prefix information? How do you compute this prefix information? That for every point, what is the total number of X up to that point? From the top left to that point as the bottom right. How do you maintain in every submatrix? So there are some common strategies, like if we know these few values, like if this is X, this is Y, this is Z, then this value basically becomes X plus Y minus Z. Why? Because X will basically include everything in this range, Y will include everything in this range, and common in both is this part which you have to subtract now. So you need to basically find out this thing and subtract it, because this has been counted twice in X and Y. So you take X plus Y and then you subtract Z. So you take the entire X, this part, then you take the entire Y, this part, and then you subtract Z, which is this part. So in this way you get that entire thing, that what is basically this summation, this thing and this thing. I missed one thing, which is you need to add this thing also to it. So over there plus basically the ijth one. So this thing, whether the grid at ij contains X or not. If it contains X, then 1, otherwise 0. So this becomes your expression. So sum X of I minus 1j plus sum X of ij minus 1 minus sum X of I minus 1j minus 1 plus this particular expression, giving you that 1 or 0. Okay, so you can code this out, code this down. So how I've done is I've handled the first row and first column separately in these things. This is just a special case of the later things. So from the first column and first row onwards, what I've done is I've basically formed that summation that, hey, I minus 1j, ij minus 1, whatever is the summation, I've subtracted I minus 1, j minus 1 from that, and then I've added if there is another x on. If there's another x, I've added something. Same thing for y. I've done the same thing for y, and then I've checked, hey, if both are the same and if num_x is greater than 0, you can do in either order, then C++, C starts from 0, and finally I return C. That's it. It's just an implementation kind of question, and a lot of variables, a lot of parameters, you can say. You just have to hold your nerves and do it. That's it. So yes, if you follow this basic approach, it's mostly good in terms of your time and space complexity. Happens in milliseconds and space looks good. So yeah, that's where we are. Now moving to the last problem, which is of course the best problem. Last problem says, hey, we need to construct a string with minimum cost. So we have to construct a string target, and we can use these words. We have to keep on appending some words from here and form this target. And I think you can use a word any number of times. You can take any word from the given set of words and append that to your current string. In this way, by appending, you can form the target, and you have to perform any number of times, including 0. Like if you perform 0 times, you can't form the target, I believe, right? Because the target's length is at least 1. So yeah, And if it is impossible, then you have to return -1. So how do you solve this problem? What are the approaches to solve this problem? One is you take the words and you keep on adding. Somewhere for every step you have so many choices of words. So if you basically say at each step I'll basically make choices among whatever options I have independently, that somewhere takes you in the exponential route. It's possible. It's possible through the exponential route, but you know that it won't survive for some larger values of n or word lengths. So then what are the other ways? In some hashing ways, etc., you can think. But basically, whenever you have this kind of an approach, where, hey, what can I start with? I can start with A. So I have these options with me. A, B, D, E, F, A, B, C. Now how do you filter these options? There has to be an indication that I am starting with A, these are the options. Now there has to be an indication that, okay, I have B next. So which options are satisfying that? Instead of 2, you may have, let's say in words array, you can have some 1000 words or 10,000 words. Now how do you get those relevant words which can fit over here? Gradually, by looking at your string, how can you say, okay, these words can fit in the best time complexity? Instead of reading all the words once again, how can you reach that information? For that, the most popular data structure is Trie. It's Trie. So you can look at this. A, B, D, E, F, A, B, C, D, D, E, F. You have these things. A, B, D, E, F, A, B, C, D, D, E, F, and E, F. Right? D, D, E, F, and E, F. So it gets stored somewhat like this. You have a root, and from there, at A you have something, at B you have something. You can name it as a, yeah, at A you have something, at B you have something. You have these possibilities. First character can be anything. The first node below the root represents your first character. Then you can have all these things, D and E. Yeah. Now the next thing, if I look at basically this possibility A, B, C, how will this be stored? This will be stored something like this. From A there will be a node for B, and from B there will be a node for D. And similarly for A, B, D, E, F, you can have, so this is, you have to somewhere mention that, okay, there is some end over here. This is where one string is ending. And instead of just maintaining that it is ending, you can mention the cost as well. Now the cost is given that ABC has cost 1. So you can mention this cost. Now ABDEF has a cost of 100. So you can maintain that. So D, E, and then F. So F has a cost of 100 over here. Now you see over here you basically have D, only D. Only D means you have to take this D, which comes right after the root. It has a cost also of 1, I think. D has a cost of 1, yes. D has a cost of 1. Now DEF and EF. DEF has 10. So for D you can form E and then F. So you form, you get the length that is 10. You get the thing that is 10. And for E also you can basically reach EF. EF has 5. After E you can have F, which has 5. Now it can happen that, okay, sometime you may get another string. Let's say you get something like this, DEA. What do? Along DE you already have something, so from E you extend a different thing, that is A. So from the top you keep on coming when you have, and there you write the cost, whatever is the cost. So in this way, in one structure you can maintain all the words. From top to bottom you keep on reading, you will get one word. Now when you come to a certain node where a word is completing, you will see the cost is mentioned. You will mention that cost. In all the other things you can mention cost equal to -1 to tell that there is no word ending over there. Like over here you can say cost equal to -1, cost equal to -1. These are all nodes. So if you can look at the basic implementation of tries. So in each node, we basically maintain this information that, okay, now you have come here, what is your cost? What was the cost for this word from the top to this bottom? And we also maintain an array of 26 places. Why? Because you have 26 characters. Each place represents a character, something like this. A, B, C, D, whatever, up to Z. Now for B, I can say, okay, if I want to take the character B now, to go down, I'll basically go this route. This will contain the address or the reference for the next node if I take the bth character. So if I take the bth character there, then I'll basically store the address where it will take me, the node where it will take me. So in this way, using the characters, whatever A or B I have, I can go to this array and go to the respective node. If no node is there, that means I have no such word. If I'm basically, let's say, looking for B and there is no B over there, I'll basically see a null over there. And then I'll conclude, okay, there is no such word which had this thing. Then if I want, I can create something, because if I get a new word, I'll create that kind of a thing over there. So yeah, that is it. And then I can store all the words in this way. The way I've stored over here, I can store all the words. And when I want the answer, how can I get the answer? I can say something like this, okay, you want A, B, C, D, E, F, A, B, C, D, E, F. So start character by character. In your try, start from the root. First go along A, you reach somewhere, go along B, you reach somewhere. Then if you see, okay, there nothing is ending over here, then again go another step. Go to C, you go somewhere. Now if you see, okay, some word is ending over here. Now this ABC can be your word, may not be your word. So you can say, okay, something is ending over here, very good. Now see that the remaining thing can be taken care of by other words themselves or not. So you can say, okay, let's complete up to here through this word. Whatever is the cost, C. Let's consider that over here that cost is whatever cost is there. Let's consider that. And now start the same operation from DEF, from the root. From the root, see where is the D, where is the E. Let's say, up to D only you have something possible. So up to D basically take it, but there is a cost. Now is this the only option you're taking? No. You basically say, okay, for this you will say cost plus, ABC's cost you have found out. Now cost plus whatever is the cost of DEF. You will find that out. Basically from there onwards to the end of the string, you find out the cost. This becomes one case. Another case is, let's say ABCDE was some word. So then this also had some other cost like C dash. So take C dash plus, then find out what is the cost of only F or whatever is the remaining part of the string, and take the minimum out of these. So you'll have multiple options, take the minimum. So we are depending on some smaller versions of this particular problem, some which take basically smaller strings for itself, and hence we can say there is a dependence across subproblems. This is the first indication of DP. So here we are basically saying that, hey, DP of our str, our answer, str some I to the end, that is some suffix. We are finding out the answer for some suffix. That is going to be the minimum of all those j such that str I to j or I to j minus 1 is a word. Let's name this str as something like x. So minimum over all those x such that this is a word. Basically say the minimum is the cost of x plus the answer, the DP for str of j to n minus 1. So this is what you can basically store as a DP state of DPI. DPI represents, I can term this as answer. answer, answer. So DPI represents what is the answer for the string starting at index I. If there are no such options, if there is no such j such that I to j minus 1 is a word, then this becomes minus 1. I mean, then this thing basically becomes minus 1. Otherwise, we will find out the minimum. So this is the recurrence we found. And who will give us this information, that what are the j for which this is a word? The trie. We get this information from the trie. We get this information from the trie. So this information we can get from the trie, all the words, basically we can get all the words from the trie in big O n time. So we can form all of this in big O n time, and for each state thus we take big O n time. So here the time complexity is basically n states multiplied by big O n per state for going through the trie and finding out all the words. So the worst case is big O n into n, which is big O n square. Now your n is given up to 10 to the power 4, 5 into 10 to the power 4. Your words dot length, that is the number of words, that is 5 into 10 to the power 4. So yes, n square is a bit larger, but the thing passes. The time complexity basically allows us, the time limit allows us. I can show my submission, which probably tells me that it is the best time complexity and best space complexity. Now either test cases are weak, or this is the best solution possible in this approach. This is the best I could think. If you have any other approaches in mind for any of these questions, better or worse or of the same kind, or you want to ask, or you want to share, or you want to flex, whatever, you can basically share in the comment section and let me know about that approach and what your thoughts are around that. So this is one way of solving this. Now let us look at my implementation. What I usually do for trie questions is I form a class for a trie node that contains those two important things, the cost and the next array. Now next array is of type trie node because in whatever A, B, C, D, it basically contains a trie node wherever. Okay, yes, in the next I basically created this array, but initially they contain 26 nulls. Now when I actually go into them, then I create the new nodes if needed. So this is my basic trie node structure. This is usually the template for any trie question. I'll have a function to insert things into the trie, and I'll have a function to get things from the trie. This is basically what iterates the trie and gets things. Each of these you can basically write in your main function only, but if I follow this template, so basically I'll keep a class for the trie node, and I'll keep something over here for this insertion. I'll keep a function for insertion, and I'll keep a function for getting the answer. So let us first look at this, the basic thing that I'm doing with this. So I'm forming a root, and then I'm calling this insert function saying that start from the root and store this word. I'm sending each word as a character array and the cost of that. So I'll store the cost at the end of that word, and then I'll initialize an answer array. I'll fill that with -1, and then I've formed the target, I've converted the target to a character array, and now I'll say okay. Len minus I, basically from the end of the string to the beginning. I'm doing this. Why? Because from each string, from each character, if you look at this DPI depends on DPJ. What is this? This is basically DPJ. This is nothing but DPJ in the same way. So DPI depends on DPJ. J is greater than I. So for, I represents a bigger string from I to the end and from J to the end. J is located later. So I to n-1 and J to n-1, I to n-1 is bigger. So I to n-1 depends on J to n-1. So DPI depends on the bigger values, the answer to the bigger values of I. So that's why I can solve from the right. That is the tabulation approach. So if you have not yet looked at my DP series, you can look at that. I'm basically solving and sharing the solution approaches to DP problems from the CSCS problem set. You can take a look at that playlist. There is a video where I've discussed the basics of DP. You can look at that and then look at how I'm applying that in all the problems. So yeah, we can apply the tabulation approach over here. So that's what I'm doing. I'm solving this from right to left, and I'm passing this answer inside for updating the answer array with the later answer values. And then I'm returning answer 0. Answer 0 is my final answer. So if we look at the first thing, insert new word. So from root, I'm going how many times? Basically, as long as I have some character in that. Okay, this is the insert new word. So I'm going through this character array. And what am I doing? I'm basically saying, okay, if the next node that you have to visit is null, then create a new node and assign that. Don't do it always. If there is already something, then use it, right? So it's something like this. Over here we saw that if you already have something like you want to add DEF when already D was there, so go along D and keep on adding. Similarly, while adding DEA, you already know that DE are there, so go along that and then over here attach this thing. So don't add new nodes where already you have nodes available. That's why I'm checking this. Hey, is it null? Then only I will create. Otherwise, I'll reuse it. So card is equal to the next node. And then I++, in this way I reach that final node along this word. So I've inserted this word through the nodes. For a 5-letter word, I have already inserted or traversed 5 nodes. And at the end, I'll say, okay, if the cost is -1, then update the cost. If the cost is not -1, then get the minimum, whatever is the minimum. So math.min car.cost, cost. Which means that if the cost is -1, that means it hasn't been updated till now. Or if the cost is bigger, then update this cost. This is how you can insert new word. How can you get the minimum cost along the trie? So start from the root. Through car, basically take it downwards. So car, take it to car.next chi -a, and if its cost is not equal to -1, that is you can end over here. Car.cost, there is some word ending at car. How to prove it? Basically, if it is not equal to -1, and if it is possible that the remaining string will be taken care of by other words. Either your string is finished, this is that condition I equal to n-1 means your string is finished, or answer of I+1 is not equal to -1 means I+1 onwards there are strings, some strings have taken care of that. You already have a valid answer for that. Then you can say, okay, you will combine this cost, car.cost, with that answer I-1, or basically 0 if I equal to n-1. So new cost equals to this thing, car.cost plus that thing. The same expression that we found over here. Our cost plus the remaining thing, that is answer of I+1 or whatever. So then we are basically saying update it if that current cost is -1 or bigger, then update it. So in that way we will get answer x for every x. I have stored x over here, x equal to I, so that I can update it here. That's how you get the answer. Finally return answer 0. You start everything with -1, so if you get nothing, then you return -1. So that's how you can solve the 4 problems of today's Leetcode contest 405. Let me know if you have any doubts, any questions, any implementation queries. Otherwise, see you in my next videos. You can check my playlists for previous contests as well as for topic-based problem sets like the DP problem set. And see you all in upcoming contests. Take care, keep coding, and become masters in the sport. Goodbye.